A very warm welcome from Physics for Students and welcome to this new episode on what is a partial differential equation. Well, I just wanted to make this video for the single purpose that partial differential equation seems to be a little bit difficult to solve, and compared to the ordinary differential equation, partial differential equation seems to be a little bit complicated. However, this is not so. So this video will give you a very basic idea, the conceptual development on solving a PDE or what is partial differential equation. Those who are watching this video must be aware about ordinary differential equation as PDE is a mathematical equation. So I hope that you have already seen my previous videos on ordinary differential equation. I won't be giving much of an example on the PDE part. However, this would be basically a conceptual approach on understanding what is a partial equation. So we straight away get to the definition of what is a PDE. A PDE is a mathematical equation that involves two or more independent variables, an unknown function which is dependent on those variables, and partial derivatives of the unknown function with respect to the independent variables. Now, as you see in this definition, particularly I have written two or more independent variables in red because this is the most important part. So we will come across, as we proceed with the video, the basic underlying difference between ordinary differential equation, which I have created few videos on the rules and what is the concept of derivative, is that in a PDE or a partial equation we involve two or more independent variables. So here is another one which says that we sometimes come across quantities and functions which are dependent on several parameters. Then it is more useful to use the change in function with respect to a small change in a single or few parameters. This is called partial differentiation. Now, when a function is dependent upon several parameters, that means it depends on definitely two or more. So anything which is dependent on two or more is where we use partial differential equation. You might be wondering why we use the word partial instead of complete or full differential equation. We will come to that and we will explain to you. Now, we sometimes come across quantities or factors that are of more than one independent variable. We find a case, this one, a case where y depends on two or other variables. So this is one which depends on one variable. As you see, x is just one variable when this u equals to f of x depends on one. However, we can compute using the limit formula and doing an ordinary differential, and we get to this. Alright. Now say for example we come across this kind of an equation, u equals to f of x and y. So as you see that this particular equation, the second part at the bottom of your screen, contains more than two variables. So the question rises that how do we solve it, right? So this is the basic starting point, that the first function is dependent on one variable while the second depends on two variables. So if we get a kind of a function like this, y equals to f of u and v, we can write it simply as f y equals to u multiplied by v, and if we treat v as constant, right, and differentiate with respect to y, we get this one, dy sub v equals to v du. So here we treat v as constant and we differentiate with respect to u. I think this is quite common, you know this. So here it is red, I have written it red, that u is constant. So we take the same expression, and here again if we treat u as constant and differentiate with respect of v, we get this. So the subscripts I have used here are to show which quantity has been taken and constant. So we indicate that the differentiation has been performed only partially. So you understand now the significance of using the word partial differentiation, because we have not fully differentiated. We indicate that the differentiation has been done only partially, not fully. That is, it has been performed only with respect to one of the independent variables. So you see here the first one uses u as a constant, right, and second one uses v as constant. So in both the cases we are doing this. So here is the same thing. So now you see that this equation can be written as this. So this curly d, it is a Greek letter which actually shows that we are performing partial differentiation. So here what we have done, we have substituted the value of v from the left hand side to the right hand side, which you have earlier seen that we have used the subscript. Similarly, you see I have written here u and v in red, so that you understand the value of u has been substituted. So these two, what we have done is that we have put in the values of v and u respectively, and we got to this, and these are called partial differentials. So you understand now why we are calling it partial differential, because we are not differentiating this equation completely, rather we are using one as a constant, differentiating, and again keeping that same constant we are using the second one and we are differentiating it. So that is why we called it partial differentials. So this is done by substituting the value of v on the first box, which is on the top of your screen, and by substituting the value of u you get on the bottom of the box. So that is the second part. So now note that the total variation of y depends on both these things. So I have written right on the top, total variation of y depends on both these things at the same time. So if both things are varying, the real dy should be written as this one, which is right at the middle of your screen. Dy equals to del y upon del u du plus del y upon del v dv, and this is actually what is called total differential. Sometimes in some of the textbooks you might find this one, which is right at the bottom of the screen. So I just thought to give you an idea, because in case that you get to know about the second one, you might get confused. So let us now look at the same concept of partial differential in a different way. So a differential is a small change in some value. For example, if we get to this equation, f of x equals to x cubed plus 4, and if we take a derivative, so we get to this, df by dx equals to 3x square, which can be written as this. Okay. So a partial derivative of a multivariate function is when we look at the instantaneous rate of change, given that we are only carrying one of the variable while holding the other constant. So let us look into another example. So you see here we have written f of x and y. So you see that there are two variables x and y equals to 4x raised to the power 6 plus 2xy squared plus 3y cubed. So we can now take x and we can keep a y constant, and that is why we have written by the rule we can use this and write it as del f by del x equals to 24x5 plus 2y squared. On the second part, I leave it up to you. You can tell me in the comment box what it would be. So now if you are keeping the x as constant and we are doing a partial differential, what would be this? And I can tell you what is the 9y squared. So if you can solve it out, this is a kind of a small exercise, you can let me know. So a partial differentiation is a small change in some value, given that we are changing the input in the only one way. So now you can understand then when we get this kind of an expression what we do. So we differentiate x and keep y constant, and then we differentiate y and we kept x constant. However, this entire term of partial differential is denoted by the curly d. So whenever we are using it, we can understand that it is called a partial differential. So on the right hand side, this equation I have kept it incomplete so that you can solve it and let me know. So we can make a third approach. I am giving 2 or 3 approaches so that things become clear to you. So we say, for example, have this function f of x equals to x squared. So using the power rule, what we can do is that we can get into this, right? So I'm using the prime notation. If you remember my previous videos where I have explained the reasons of using different notations. So f prime of x equals to 2x, right? Now if we get something like this, f of x and y, two variables, equals to x squared plus y cube. So the question rises that how do we do? So to find its partial derivative with respect to x, we treat y as constant. So here what you can do, you can just imagine y as some kind of a number like 2 or 7, and we do this. So you can see f prime of x, we have used the power rule, and the same, it comes to 2x plus 0, and which we can write it as 2x. So here what we can tell is that the derivative of x squared with respect to x is 2x. We treat y as constant, so if it is y cube is also a constant. So if I take a y cube, say for example 2 or 7, so 2 cube would be 8, 7 cube would be 343, whatever. So it is also a constant, and we know that the derivative of a constant is 0 by the ordinary derivative rule. So to find it partial derivative now with respect to y, we treat x as constant and we get to this. So this one is where we have kept y as constant. Now you see what I am doing is that I have got f prime of y equals to 0 plus 3y squared with the same equation, and we get to 3y squared. Here what I have done is that I have kept x as constant, right? So here on the first we have kept y as constant. On the second we have treat as x as constant, so x squared is also a constant, and the derivative of a constant is 0. So therefore the derivative of y cube, now in the second case, the derivative of y cube with respect to y is 3y squared, which is right in front of the screen. So that's it. So this is a pretty simple example. So all you need to know is that you need to treat all other variables as if they are constants. Yeah. So then you can just go on one by one, component by component, and you can partially differentiate it. Given the second approach, I would just like to tell you this f prime of x, which is right in blue in a circle, let us keep it for the time being f prime of x, because I will show you that this f prime of x now and slowly gets into the curly d, which is the sign of the partial differentiation. Now what I will do, all those equations etc., it was all figures and kind of mathematical notations. I will try to give you a geometric representation. So geometric representations are always easier to visualize and understand. So for example, let us take this to be a cylinder, right? So right on the top on the left hand side, this yellow is the radius, which changes a minute change. It goes the red one, which is shown as r plus. So what we will do is that we already know that the volume of a cylinder is V equals to pi r squared h. That is the volume of a cylinder. Now if we use, say for example, two variables which is changing like r and h, so we can write function of r of h equal to pi r square h, which is the volume cylinder, but I'm using two variables, so I'm writing this one. So to get the partial derivative with respect to r, we take h as constant, and as r changes we get to this one, and then further this one, right? So the derivative of r squared with respect to r is 2 pi, and here we have kept pi and h as constant. So here you see that r changes, right? So the derivative of r squared with respect is 2 pi, and this one r changes. So what we can tell, as r changes by a fraction of amount, note that this one, this yellow and the red one, which appears on your screen to be quite a significant change, Actually, while using differentials or calculus, we don't make that kind of a change. It is a minute change which is very negligible, which cannot be observed by naked eye. So as r changes, that is radius changes by a fraction of amount, the volume, how much it changes by 2 pi r h. So this is a kind of a visual representation where we are calculating the volume of a cylinder with the same formula pi r squared h, but we are using two variable r and h. In the first case, I have kept h as constant and we are changing with r, so f prime of r equals to pi to rh using the same formulas of ordinary differential equation, which comes to 2 pi rh. Now for example, I take another case. The same cylinder, we keep the radius to be same and the h again changes from the black bar to the red one, h plus. Again, I will like to tell you that this one it is not that what I would say a very big change. It is a very minute change which cannot be observed by eye. So now we take the same one, volume of a cylinder equals to pi r square h, right? So we take the same two variables. So we use f prime of h, that means we are differentiating or partially differentiating the height as it changes, and it leads to pi r squared. So here you see I have marked in blue that as h changes, that means I am keeping r as constant. So we can say that as h changes by a fraction of amount, the volume changes by pi r squared. Here pi r squared are constant, the derivative of h with respect to h is 1. So we can say as only the height changes by a fraction of amount, the volume changes by pi r squared. So these are the two geometric representations so that you can understand the concept of partial derivative using the volume of a cylinder. In the first case, the radius changes, the height remains constant. Here the height changes and the radius remains constant. A third geometric representation would be something like this. So you can call it as a volume, it's a cube with a kind of a square or a prism cut inside it, and the sides, so yes, the volume of a cube with a square cut out from it, so the sides are this. And if we take this kind of a scenario where we get three variables, because we are dealing with a three-dimensional object x, y and z, then what I can do, if I partially differentiate f prime of x, we get to minus 2xy. With y we get to 0 minus x squared, and with z we get to 3z squared. So this is again a kind of a kind of an example which shows that how a volume of a cube, once it changes, how we partially differentiate with x keeping yz constant, y keeping xz constant, and z keeping xy constant. So just note that f prime of x, which I have used, is basically meaning that the partial derivative with respect to x. So this can be written as this, del f by del x equals to 2x, which is the same as f prime of x equals to 2x. So if you take something like this, say for example x, y and z with an equation x raised to the power 4 minus 3 x, y, z. So first we take x and we get this one when we partially differentiate it. Then we take y and once we partially differentiate, we get minus 3xz, and then we get z and we get minus 3xy. So this is a kind of a pretty simple example that how do you partially derive when there are two or more variables. In my next videos, definitely I would be giving more examples of how to actually solve kind of a partial differential equations, but I think this is quite a nice concept which will build it up. So just to summarize, what we can tell, that if we have a multivariate function, let us assume this one, fx equals to x squared plus y squared, we can differentiate it with respect to one of the variables. So it comes to this and it comes to this, right? So but partial differential, this is a special sort of differentiation. So yeah, you see this one. So on the left hand side we use the ordinary, and on the right hand side we are using the partial derivative. So partial derivative is a special sort of differentiation in which we consider all other variables apart from the one which we are differentiating with respect to others which are kept to be constants. So this gives you a pretty nice approach, basic understanding. So we need to understand one thing, that using whatever the rules that we do, partial differential is when we are getting one or more variables, especially 2, 3 and 4. And I hope you understand that partial differential equation is crucial in terms of physics, in terms of heat equation, Laplace equation, Navier-Stokes equation, and especially when we are learning Einstein's general theory of relativity. Why? Because we are dealing with 0, x, y, z, or you can say t, x, y, z, where the three spatial dimension and one time dimension. So that means we are dealing with one or more variables, so we need to use partial differential equation. I hope you liked my video, physics for students. Do like, subscribe, and please press the bell icon so that you get all the subsequent notifications that I'm making on the channel. So my next video would be how to solve partial differential equations, where there will be sufficient examples given, starting from a simple one to a complex one, so that things become much more easier and you can understand pretty well. Thank you very much. Do let the exercise go on which I have shown in the video, and you can put up your comments. Thanks very much for putting up all the comments previous. I'm thankful to all the subscribers. Do like, subscribe, and share my channel, and I wish you all the best, and stay safe, stay happy, and have a nice day ahead. Thank you very much, and bye.